Consider the region R bounded by the parabola y equals 49 minus x squared and the x-axis. To find the volume of the solid when R is revolved around the x-axis, using the method of disks, evaluate the integral. So it wants us to set up the integral. All right, so what I did is same thing you can do is I went out to the disk washer link on the home page, and I put in our function, 49 minus x squared for my f of x. And the other one says the x-axis. That means y equals 0 or g of x equals 0, because that's the x-axis, um, right? The x-axis is right here. This is the x-axis. This is the y-axis. All the points on the y, all the points that have a height of 0 that go through the y-axis at a height of 0, right? That's the line that goes through the y-axis at a height of 0. It's the x. It's better known as the x-axis. So that's why I put that in there. All right. And so you can see that it automatically graphs this as f of x up here, and this is g of x down there. And what it does is it sticks in automatically for us. I told it to put in washers and disks. And oh, I told it also, how do we know where it goes from? You got to adjust these A and B on the bottom. Well, it's got to go from -7 to +7. How do I know that? Because that's where it's going to be 0. It's going to hit 0 here and here at over 7 up 0 and back 7 up 0. How do I know? Because if you take this equation, you put in 7 for x, 49 minus 7 squared is 49 minus 49 is 0, or -7, same thing. Okay? So that's just where the y is going to be 0. So, and then I asked it to graph it, and what it does is it fills up. There's a partial image of the three-dimensional shape. Right? We're finding a volume. It's a three-dimensional shape. There is the volume. We fill it up with disks. See how these are the edges of the disks. You can see the disks here that are filling it. Now, you might say it's not perfect. No, there's gaps, as you can see, but that's just because I've only got it set on 7 disks. We're gonna, whenever we do an integral, dx, that's infinite disks. And if you have infinite disks, they're infinitesimally small and they fit the curve perfectly. This is just, that's what calculus does. That's what the integral is. It's the antiderivative of infinitely small pieces. Remember, we started this course with limits. Limits. It's all about limits of infinitely small things. So these disks, so then the question is, how do we figure out the volume that these disks take up? Well, what's the volume of a disk? That should be a first and important question. Volume of a disk. Well, it's pi r squared. Well, here, let me do it this way. It is pi r squared, but it's the area of the top. It's pi r squared times the thickness. Area of the top times the thickness. So you can see the top of each of these disks is clearly a circle. So we're talking about a circle. A very good circle, was it? So a circle, and what's the area of a circle? Pi r squared. But then the circle is going to have some thickness to it. Oops, I wasn't in my tool. I thought that I was. All right. So it's going to have some thickness, and that's either going to be dx or dy. So we can see each of these disks, make this a little bigger, the thickness here, let me get rid of this, is dx. That's how thick each disk is, dx. That's a side view, right? Do you understand? That's grabbing this and putting it right there. It's a side view. Each of these disks, the thickness of each of these disks, this is the x-axis here. This is the y-axis. Each of these disks has a thickness of dx. See how they're going along the x-axis? So then the volume of every disk is going to be pi r squared times dx, because that's the thickness of each disk. So we're going to want to add up all these disks that are in here, from where? Oh, this right here goes from -7 to +7, and it's pi r squared dx. But then the question becomes, what is that radius? Well, the radius of each disk. What is that? Well, the radius of each of these disks, we can see it right here. The radius goes, like I'll take this one here. That's the radius, isn't it? Can you see it right over here on these disks? But remember, the radius of a circle is from the middle of the circle to the edge, right? Yeah, like you can see right here. Just point to this. This guy is a radius because he goes from the middle of the circle to the edge. That's a radius line, isn't it? See that? So what's the radius line? How far is that? Well, that's the y value. That's what that is. Whenever you go from the axis up to a point on a graph, that height is the y value. What is the y value? Well, that's the function y equals 49 minus x squared, right? So is that right here? This is y equals 49 minus x squared. So that's the y value. So the y value is the radius. Especially you can see it on the 3D view right here, right? From the middle to the edge, from the middle to the edge for each of these disks, from the middle to the edge, the radius of each of these disks is the y value of the function that it's hitting. So that means this is y squared dx, right? The radius squared is y squared, but we can't have y and x mixed, so then we got to fix that. That's got to be the integral from -7 to 7 of pi, and then we come to y squared dx. What is y? Well, we just said right there, y is 49 minus x squared. That's the y value on that. And so there we go. There's the setup of the integral that'll figure that whole volume. And that's what we got right there. So that's the integral. See how that is? Because we're adding up. Remember that's a big S. We're adding up. We're summing up all these disks to fill up this three-dimensional shape that we rotated around the x-axis. And so that total volume is going to be a sum of all those. And each of those is a disk, which is pi r squared around times dx thickness. And the r is the radius is the y height up to the function. And so there we go.